All right, so hi everyone. Welcome to discussion 11. Today we're going to talk about graph algorithms. So started about graphs last week, right? And I'm not sure. Yeah, hopefully everyone can hear me okay. Okay, yeah, can you hear me okay? Okay, cool. All right, so for discussion 11, yeah, we talked about graph algorithm or graphs last week. Now we're talking about graph algorithms, in which we're going to be using graphs to solve certain problems. So let's get to it. So the first thing is we're going to talk about objectives. So we're going to talk today is shortest path algorithms. So that's Dijkstra's algorithm to find single source shortest path from Bellman-Ford, which is another single source shortest path, except it solves some problems that Dijkstra's can't. And then we'll talk about MST, or minimum spanning tree. If it's next time, then I'll make sure we get to it, or I'll try my best to make sure we get to it. And yeah, so shortest path algorithms. So today we're talking about single source shortest path. There are other problems. So like all pair shortest path is another problem, which is shortest path where like single source shortest path means you have a single source. So you start at some vertex and you want to know the shortest path to like every other vertex or any other given vertex. Both pretty much use the same algorithms. So yeah, single source shortest path means you start at a given vertex and you try and go to either one other specific vertex, you want to find the shortest path to that vertex, or the shortest path to all other vertices. And that's why we call it single source. There's also all pair shortest paths, which is you want to know the shortest path between any two vertices. Like if you start at some vertex, you want to know the shortest path to like any other given vertex. And today we're talking about the first one. The second one also, there are different algorithms for that, like there's Floyd-Warshall, which can have negative weight edges and can detect negative weight cycles. There's also Johnson's algorithm, which is another all pair shortest path, which can't detect those, but does run a bit faster. And we'll notice in single source shortest path, there's another thing. There are two other algorithms, which one runs faster than the other, but can't necessarily detect these types of things. So, okay. So for single source shortest path, like I mentioned, it's from a single source to all other vertices. And specifically for unweighted graphs, it's just a BFS. And it's actually pretty funny because we can actually, for example, if you run Dijkstra's on, which we'll talk about Dijkstra's in a few minutes, but if we just ran Dijkstra's on an unweighted graph, it would basically just run BFS. So that's kind of interesting. So really, like Dijkstra's is kind of an extension of BFS in a way. Although, it's much more general. So BFS, again, this really works on unweighted graphs because what we're essentially doing, and the reason why Dijkstra's is essentially the same is because we're just treating it as if the graph has every edge weight of 1, and it just ends up running the same. But that's how we do it for single source, and I think we saw some of that last week. But Dijkstra's runs in O of V squared time, or you can input the heap, and it's O of V plus E times log V time. But the way it runs is it can run on a weighted graph. So not just unweighted graphs like a BFS can. It can run on weighted graphs, which is pretty cool, right? And it can give us a single source shortest path, so shortest path to all vertices. But the problem is you cannot have negative weight edges on Dijkstra's. It just will not work. We'll see why, but yeah, Dijkstra's doesn't work in those conditions. But thankfully we have an alternative, which is Bellman-Ford, which as you can see runs a bit slower. It runs in O of V times E time, but it can have negative weight edges. And another nice thing is it can detect negative weight cycles. And if your graph has a negative weight cycle, there is no shortest path, because if you wanted to, like, let's just draw an example really quickly. I just want to kind of show you what I mean. So if we have something like this, let's say we have like negative 100, and then like these edge weights are 1 and 1, then the shortest path, right, from this guy to this guy would be negative 100 plus 1, that's negative 99, plus 1 plus negative 100 plus 1. Oh, now we're at like negative 197, I think. Yeah. So like we can just keep going around. So it's infinitely small. So there's really is no difference. But Bellman-Ford can detect that and tell us that. So that's good. But Dijkstra's can't. So we'll kind of see how those algorithms work. So first, let's talk about Dijkstra's. So what is Dijkstra's? Well, Dijkstra's, like I mentioned, is single source shortest path, but it doesn't work with negative weight edges. But that's okay. Like we see this a lot of times when you're dealing with graph algorithms or graph problems, you aren't going to have negative weight edges, so it's fine. And in this case, we actually see exactly that, right? There are no negative edge weights, so we're good. And yeah, and after I'll mention this later. So never. Yeah, so you can see here, it doesn't even matter as a directed graph, it's still okay. And what we see, right, is the way this works is first we initialize the graph. So I guess I will mention what I was going to say because it's kind of bothering me, but yeah, you might think to yourself that like for negative weight edges, you can just make them positive by adding some constant, but it doesn't quite work that way. But maybe you can think about that, but that's not really relevant. So sorry I mentioned that. But anyway, so back to the point and Dijkstra's algorithm. So you have initialization, and what you do is first you just basically make these arrays or maps or however you want to implement them. You have these here. So first of all, you have your keys, which are just your vertices in your graph, basically. And here we have S, T, Y, X, and Z, because those are the keys. And you have your V for that. And what V is just visited or not. So all of them have not been visited before we start. So they all start as false. The next one over is distance. So it's the distance from your source, which is what we're looking for, because remember, it's like only one. It's like one source shortest path, right? So single source shortest path. So we are wondering what's the distance from that source to this other vertex. So originally it starts as 0 for S because it is that source, and the rest of them are infinity because there is no path so far. And this actually keeps track of the predecessor. So predecessor, it just means in the path that you're wondering about, what comes before it. Like in the path to get to that vertex, what comes before it? Well, originally there is no path from S to any other vertex. So the all star is null. There's nothing that comes before it in that path. And S to itself, we can just say null. Okay, so that's how we initialize it. We have basically our vertices, visited, distance, and predecessor. So what do we do next? Well, we're going to do relaxation. Well, first we do S, then we're going to relax. We're going to do what we call relaxation. So we're going to relax the edges. So we select S, right, because it's our source, and we say, okay, this is the vertex we're starting on, and we're going to relax the edges. And what we mean by relax the edges is, well, first we have to mark S as visited, and we say distance to S is 0. Then we're going to go ahead and say, okay, these edges from S, right, to some other vertex, we're going to say, okay, let's go ahead and compare these to the distance so far. So basically, distance to get to S from our starting point, but that's 0 here, plus our distance, plus the distance from S to T here, right? If that's less than the current distance that we have from S to T right here, then we're going to replace it. And in fact, that's the case. So we're going to replace it with 10. And the same thing with Y. So we're going to replace this with 5, like 0 plus 5, which is just. So let's see. Let's go ahead and go through the slides. In the first iteration, the distances to Y and T and Y are relaxed, like I mentioned. So we have 10 and 5. The way Dijkstra's work is it's called a greedy algorithm. And we'll talk about greedy algorithms next week. But the idea is that it's just always going to choose the minimum at each step. So notice for Y here, that's the smallest, right? It has the smallest distance. So it's the shortest path to get from S to any other vertex that we know of so far is 5. So that's what we're going to pick. And we're going to say, okay, this guy now is part of our shortest path. So after relaxation, we're going to take the shortest distance of each iteration. So now Y is included, and we're good. And we say, okay, now we visit Y. So now we visit Y, and we say the predecessor. Oh, we also updated the predecessors before, because whenever we update distance, we also have to update the predecessor of whatever made that distance smaller. So here we do that. And now we do another relaxation. Now we're going to relax the edges that basically the Y is interested too. So like the things that come out of Y, right? The edges that come out of Y, we're going to relax those edges. So we're going to relax this one, and this one, and this one, And in fact, it's actually going to update something. So let's see what happens. Well, what we're going to update, notice, is that we still haven't visited any new vertices, but we update the distance. Because the distance from S to Y and then Y to T is smaller than just the distance from S to T, we're going to replace that distance here that was 10 before, we're going to replace it with 8. And the predecessor of T is now Y rather than S. And the other two are also updated because before they're infinity, so it's a lot less. So it's 5 plus 2 to get to Z, and 5 plus 9 to get to X, and that's 14. And all of these predecessors are now Y, or yeah, are now Y because Y was the thing that came before. And so notice we do our relaxation. So again, just as before, we're going to choose the minimum. The minimum here is 7, so we're going to choose Z. And then we're going to relax the edges from Z. And it's going to relax these edges. But it won't update for S, but it will update for X. The path now to X is smaller, or like the distance is smaller if we go through Z than if we just went through Y. So we update the predecessor and the distance. And now again, we take the smallest. Smallest is T. So T, we basically are saying, okay, now T is definitely part of our solution. And then we again relax its edges. And notice that distance now to X becomes smaller. And we visit X, then we're done. And yeah, the edge relaxation principle we'll talk about, but it might also be kind of becoming clear why negative edge weights don't really work with textures like we mentioned before. And the reason for that is because notice that at each step, whenever we like show something, we're like, this is definitely now part of our solution, right? Like at this step, for example, we're like, okay, yes, take Y, like we have Y here, it goes to Z. Now that's definitely part of our solution. Like when we choose Z, okay, now Z is definitely part of our solution. But the problem is that it may not necessarily be true if they're negative edges. For example, if this were like, instead of 9 here, let's say like negative, or like, well, that's actually incident to Y, but let's say that this were like negative 2 or something, and this were like negative 4, then in fact, this would only be distance 4 to get to Z. And so later on, or I guess this should be this way. And I wrote over the wrong edge. I meant this one should be negative 4. And this one should be 6. But later on, we would get a better solution, right? If you notice, because we would get a better solution to get to Z. But the way Dijkstra's works is once it has something and it's like, this is now part of a solution, it won't change it. So that doesn't really work with negative edge weights. So that's why it doesn't work with negative edge weights, even though there's no negative cycle here. So this is perfectly fine graph, but it won't work with Dijkstra's. So that's why we have element for it. But for positive edge weights, that's not a problem because distances can only go up, they can't go down. So that's an explanation of Dijkstra's and why Dijkstra's have negative edge weights. Hopefully that's kind of clear. But anyway, back to the edge relaxation principle. The whole idea of when we're relaxing edges is that at each step, we decide whether an edge, we consider whether the edge, or yeah, we consider an edge and whether the path from vertex U to vertex V, like our new vertex, is better than anything we found before. And if it is, then we have to update, right? Update the distances for that key, and we have to like say, okay, all of its edges are going to be small. If they're smaller, then we have to say, okay, the new predecessor is the new guy. And yeah, and then we just update the distance. And in code, the way we do this, right, is like we mentioned kind of in words, if the distance to get to this vertex plus like the newly chosen vertex, if the distance to get to that newly chosen vertex plus the distance to get to from that vertex to some other vertex is smaller than any distance we had before, then update it. So as an example, just going back here, like even on the first step, since when we relaxed S, since the distance from S to Y became smaller, like distance from S to S plus distance from S to Y was 5, which is smaller than infinity. So because of that, we update Y here to be 5 and its predecessor to be S. And so we just keep doing that at each step. Whenever we relax, that's what we do. And yeah, it just works by solving this problem repeatedly using edge relaxations. And until everything has been visited. And the idea is that Dijkstra's works with weighted graph, but it doesn't work with negative edge weights like we saw a moment ago, because with negative edge weights, that would require us to update later on. But once we accept something as part of a solution, we don't change it in Dijkstra's. And it works with directed and undirected graphs, which is great. And it runs in OV squared time, or like something slightly different if implemented with a heap. It's a greedy algorithm, which just means that at each step, we just choose the local optimal solution. So basically choose the smallest at that step, which is why it's called greedy. And in each iteration, we just perform relaxation to all of the edges that originate from the newly unvisited vertex that became visited. And so that's great, right? Dijkstra is really good, and it's the best we have for positive. If every edge weight is positive, it's the best we can do. But as we mentioned, it doesn't work for everything. So that's why we have something right after the poll question. But for the poll question, which of the following statements is not correct about Dijkstra's?
Two.
Yep, awesome, nice. They cannot have negative. Okay, well, and I guess we'll talk about Dijkstra some more. Then we'll talk about the next algorithm. Oh yeah, so we'll talk about implementation of Dijkstra's. Then we'll talk about the next. So implementation of Dijkstra's. So generally, when we implement it using a couple maps. So like before, when we saw our table, we had a map which contained V, or we had V, which is it visited or not, in which each vertex is a key, and then a Boolean value to indicate whether it's visited or not is the value. We have our distance map, which is just telling us what is the distance from the source node to this node, where each vertex is a key and the value is just the distance. It's initialized to infinity. Or in code, I guess you'd initialize to like maximum of integer or whatever. And then the source vertex's distance value is set to 0 because the distance to yourself is 0. I want to make sure it's selected first. We also have a predecessor map, which is just the vertex is a key, and its predecessor is value, and it's initialized to null. And then, yeah, we use that to actually construct what the shortest path was, because without it, we can still figure out what the length of the shortest path is, but if we want to actually reconstruct what the path was, we need that predecessor map. So in terms of code, here's what we do. We initialize V with all vertices as unvisited. We have distance with the source vertex distance at 0, and all others set to infinity. And P are all set to null, because that no predecessors yet. And while we have some unvisited vertex, we're going to find an unvisited vertex here that has the smallest. So we're going to figure out which of the unvisited vertices has the smallest distance value in dist. And yeah, and actually, yeah, this is exactly right. I was thinking whether I should mention it, but yeah, this is why we might use a heap. Because remember, with heaps are like heaps are priority queues. So the whole idea is, if we were using an array, we'd have to like loop through the entire list of vertices to figure out which one has the smallest distance. But if we're using a heap, we can just remove the root, right? And that'll tell us which of them is the smallest, which of them is the smallest dist that we haven't chosen yet. So that's kind of nice, because removing that versus looping through a whole array is a lot faster, because this one is log and that one's linear. And then we mark that U has been visited. And then for each of its edges, this is where the relaxation step. For each of the edges to some other vertex, like here, for example, we see Y. If it's not visited already, if it is visited, we don't do anything. But if it's not visited, then we're going to relax the distance in the table. So we're going to update the value. That's where we had the code. If distance to the current person or current node plus the distance from that current node to the next one over is less than the distance to the new node, like the next node over, then we update the distance and we update the predecessor. Otherwise, we don't. So we relax the distance. In other words, select the minimum current value for Y, new distance from like source to U plus Y to U, or sorry, source to U plus U to Y. If that's less, then we update it, and we also update the predecessor. And this is more concise code. Initialize, and then while we don't have our empty queue, right, you just keep extracting min from the queue, and then you union your set with the newly inserted vertex. Like this set is just the output, like what Dexterous is going to output. And for each vertex in your JSNC list for you, your lax libs. Okay, so poll question. So given this following table of vertices and the predecessors from Dijkstra's, what is the shortest path between S and X? Okay. Well, for these types of questions, a lot of times it's easiest to work backwards. So what we can do is we can start at the end, right? And we want to know the shortest path between S and X. So we actually can look at X and we figure out, remember, this keeps the predecessors. So if we start at the beginning, S, it's not going to give us any information. So we want to go at the end and keep looking at the predecessors until we reach S. So we look at X and we look at its predecessor. Well, its predecessor is T, so that's the thing that came before it. So X is at the end, but the thing that comes before X is T. And then we look at T, what's its predecessor? Y, so the thing that comes before T is Y. And the thing that comes before Y is S. And we kept looking until we reached S, and then we're done. There's nothing else to look at. So that's our shortest path. S, Y, T, and X. And that's how we do problems. Cool. All right, and for the next one, given this, what is the shortest distance between S and X? Yeah, sorry, if you're saying something, I'm not sure if I can.
No, I just unmuted because I'm doing it.
Okay, cool. Oh, whoops, I don't think I meant to show the answer. But yeah, if you're doing it at home, you can also try and figure it
out. 22. Wait, no. Oh, 9.
Right, yeah, 9. And yeah, you were probably going through the predecessor graph, right?
Yeah.
Yeah, in this case, just 9, because this distance here just tells us what the distance from the source was, not from the predecessor.
Yeah.
Cool. And so another poll question. Given the following graph with W as a source, what does the distance values be after the second iteration of Dexter's?
So this would this graph be considered like before any iterations, or is it considered technically after the first since it was filled with null?
So this, like what we have starting here,
Yeah.
yeah, that's after 0 iterations.
Okay. So for the first iteration, we have to visit X and Y. When we visit X, we will update it to distance of 9 and the previous being W. And for Y, distance of 5. from W, and then the second iteration, we'll need to visit Z from both Y and X, and then visit X from Y. So X from Y is going to be, wait.
Yeah.
So that's going to give you the 5 plus 8, which is a shorter distance. So we'll change it to that one. And then towards Z from Y, distance of, oh, we haven't visited that one yet. So Z from Y is 7, and then Z from X is 13, so we don't use that option. So then the distance values in alphabetical order, I have 0, 8, 5, 7, which is option C.
I think that's right. One thing I did want to mention though, so I think, yeah, you got the answer. But one thing I do want to mention is that like in the first iteration, after the first iteration, like we're going to visit.
We're supposed to pick, like only go down the
Exactly, exactly. Yeah, you only pick one. Yeah. So yeah, we don't visit X until like later, like the third iteration or something. Or the fourth, I guess. But yeah, awesome. Yep, so after the first iteration, these, and then we choose one to visit, we're going to choose Y. And then into this degree. So cool. Sure. All right. But as we mentioned, there's a bit of a problem with dexterous, or it can be, and then it doesn't work with negative edge weights because of the greedy approach. And we can see a similar example to what I showed earlier, where what it might do is it might choose S, and then it might just choose Y. But later on, there's going to be a better way to get to Y, right? It'll be like, oh, we're done. But there is a better way. Although this is with negative weight cycle. So negative weight cycle, there is no actual correct solution. But like if we consider if this were not negative 10, if we're like negative 5, for example, then the distance would just be 0, right? But that's okay. Like that's why the exercise doesn't work. But again, also even with just negative weight cycles, like this would be a negative weight cycle. If it's undirected, if these edges become undirected. With the edges directed, it's not a problem because we can't actually, there's no cycle here. It's an acyclic graph. So yeah, sorry, the green confused me. But yeah, so that's the problem with negative edge weights. With negative weight cycles, notice this is a cycle, the previous one wasn't, because now these are undirected. There's a problem because there is no optimal solution. Because we would just be like, oh, let's go from S to T to Y, back to S. And then like you keep going and you keep going around and around and around. And the best possible distance is negative infinity. There is no best. So no shortest path algorithm can handle it. But Bellman-Ford can recognize it. And so that's the thing we're talking about next. It can also deal with negative or edges. It's slower, but yeah, it is more versatile. So let's look at it. We can handle negative edge weights, negative weight cycles. And just like the extras use the distance map, in fact, it's a pretty similar algorithm. The difference is that instead of only doing relaxing some of the edges, in every iteration, it's going to relax all of the edges. And yeah, it performs exactly V iterations. You can do a slight improvement on it in which instead of just doing exactly V iterations, if there's no change between any two iterations, then you know you're done because there's like, if there's no change in one iteration, which it goes through all edges, then no matter how many more you do, it won't change anything. So you can always terminate then. So that's a slight improvement. It doesn't necessarily need V iterations in that case if it doesn't update. But in general, in the worst case, it will require order V iterations exactly. And then you might think, okay, well, that's weird because if you remember in Dijkstra's, we started with the first vertex already known, and in each step, we just included a new vertex. So why would we need V instead of V minus 1? Well, it's because that last iteration is going to show us if there is an improvement. And if hopefully after V minus 1 iterations, we'll be done. There won't be any improvements left to make because we basically choose a new vertex each time. But if there is still some improvement that's made, that must mean there's a negative weight cycle. And so that's why we do V instead of V minus 1, because that V, the last one, is there just to tell us is there a negative weight cycle? That's the idea. But the ith iteration finds any edges with, or yeah, finds the ith iteration just looks at all the edges, like every iteration looks at all the edges. And yeah, the last iteration, like mentioned, reveals there's a negative weight cycle. The order in which you access them can affect performance, but well, I guess that's something you live with. Okay, so small example here because there are more iterations you have to do. Let's start at, these are our edges, right? And each time we're going to have to go through all of them. So let's see, we initialize our map. Again, same as before. We have our distance map, our vertices map, and our predecessor map. What's missing is visited, because that's not necessary. If we're going to go through every edge in every iteration anyway, we don't care if we visited or not. So that's not even here. But we'll see that it does work with negative weights. So, okay. We're going to go through our edges. Let's go through them in this order. So we're going to go through T. We're going to see TY. So we're going to try and see, okay, does this update anything? Basically, is the distance from T to Y, or distance to get to T plus the distance from T to Y less than the distance from just to Y? And it doesn't. Like -10 plus infinity versus infinity, just above infinity. So it doesn't change anything. But the second one does. So that's the first one. Now we can look at the next edge. So the next edge is just S to T. And S to T, it's going to update 0 plus 5 is less than infinity. So we have 5. And our predecessor of T is S. So this is still part of our first iteration, because we have to visit all edges in our first iteration. Then we're going to visit the last edge, also in the same iteration. So now S to Y. And notice that the distance is 2, and 2 is less than infinity. So we're going to update it. And as I mentioned before, like the order in which you access them does matter, because like it's not necessarily known beforehand if it will, but here we can clearly see that it does, because for example, if we'd done TY last instead of first, then we would have already had the like Y, like distance to Y is -5. Versus here, because we accessed it first, after the first iteration, the distance is just 2. It doesn't matter because like if we do V iterations, we will get it to be right at the end of the day anyway. So let's do our second iteration. We do this one first and we notice, hey, it goes to -5. And then we're gonna go ahead and relax the other edges, or yeah, we're relaxing all edges, so relax the other ones. So relax S to T. And it doesn't change anything. T is still 5 and Y is still 2. Okay. So now we're gonna do our final iteration. And we're expecting no updates. If there is an update, that means a negative weight cycle. So let's see. We do this one, we do that one, we do that one. There's no changes, so there's no negative weight cycle. And so that's good. That means that there is no negative weight cycle, and this is the best we can do. So let's look at the pseudocode. So step 1 is to initialize the graph and our map. And then the second step is repeated v-1 times, and then we do the last iteration here. And the v-1 times for each edge, we have to relax it, right? We have to relax every edge. So if the distance to you plus the distance between like you and all the other things it's connected to is less than just the distance to each of the things it's connected to, then just like before, just like with Dijkstra's, we update the distance that that thing it's connected to has, and we also update its predecessor. And we're doing this v-1 times. And as we mentioned, we can terminate early if there's no change between two consecutive iterations, but it will always work if you don't. And then the last step is checking for negative weight cycles. So it checks if you would update something. So if the distance to you plus W is less than distance to you. So if there is something that should be updated, then there's an error, and there's a negative weight cycle. And the reason for that is because if we think about it, right, if there isn't a negative weight cycle, right, then that means that any path, right, the longest simple path you can have in a graph right, is just v minus 1. It's of length v minus 1, right? Because a simple path is of any path that doesn't repeat vertices. So the longest simple path we can have goes to every vertex exactly one time. You start at the source and then you go. And so because the relaxations will always add one new edge to whatever path you have, at least one, it could add more than one, but each of the v minus 1 iterations here adds a new edge to that path. And because there are only going to be v minus 1 things on that path, then at the end, if there's something even better, then that must mean that there's some edge which is like, then even though the path is already done, like there's still a better way to get there. And the only way that's possible is if there's some cycle which had a negative weight, because the distance can decrease, even though we've already found a path that gets there. I mean, that's some intuition for it. Hopefully that kind of makes sense. But that's maybe not so important. But the main thing you need to understand, or you need to realize, I guess, is just that Bellman-Ford v minus 1 iterations, well, relaxed edges, and the last one, we'll just check for negative results. Okay, and so poll question. And I'm not sure I like this poll question so much, but yeah, you can try and answer it anyway. It's able to find the shortest path in any graph with negative edges.
False.
False.
Because yeah, if there's a negative weight cycle, then there is no such shortest path.
That's exactly right. Yep. And for me, this just feels like a tricky question, which I don't love it, but yeah, awesome. Good answer. That's right. Okay, question number 6. What is the minimum number of iterations that it could take to converge to a solution?
1.
Awesome. Yeah, exactly right. It could just take 1. And yeah, it depends on the order of measures of them. So it could visit it and it could all work out just perfectly. We end up with a perfect solution. And it, unless you make a check in which, okay, did anything change? If you don't have that, it would still run v iterations, but it could have the right thing after just 1. So, okay, so question number 7, which real world example would be better fit for Bellman-Ford instead of Dijkstra's?
Three.
Yeah.
Because then you would have negative weights.
Exactly. Yep. Perfect. Okay, and now we'll talk about, I think there's some time. So yeah, we're going to talk about minimum spanning tree. So first, it's the union finds data structure, which actually I don't know why we're talking about this now. So let's skip over union find because that deals with the second algorithm we're going to talk about, because there are 2 for minimum spanning tree. Let's kind of skip over this for now. So what is minimum spanning tree? Well, minimum spanning tree is a subset of edges of connected, weighted, and undirected graph. So really, this is like, it only works in like connected, weighted, and undirected graphs. So it has to be those things. But the interesting thing it gives us is it connects all the vertices together without any cycles with the minimum possible total edge weight. So basically what this does is it gives us a tree, which is why it's called minimum spanning tree, because it's going to take v minus 1 edges, and it takes v minus 1 edges because that's what guarantees it to not have a cycle. But the main idea is also, or more importantly, it takes it puts all of the vertices into one structure, or selects all the vertices with the minimum cost. That's why it's the minimum spanning tree. It has every vertex in it with the least cost of all the edges. And the 2 famous MST algorithms are prims and Kruskal's. The union finds we saw a second ago, that's Kruskal's, and that's why we're skipping over it for now because we're going to do prims first. Both of them are greedy. And it doesn't necessarily give a unique graph unless the edge weights are unique. If edge weights are unique, it will give a unique solution, or there is a unique solution. But if edge weights are not unique, or if there are multiple edges that have the same weight, then there might be multiple correct answers for an MST. So prims, what prims is given a connected, weighted, undirected graph, it gives us an MST. So it gives us, again, selects all the vertices in the entire graph such that they're all connected to each other still, but with the lowest sum of edge weights. So like, for example, if I look at this initial graph, if instead of this is my MST, like it wouldn't be okay if I chose like this is my MST, because even though all of these things are connected, the sum of the edge weights is larger than they are here. So the way it works is, yeah, its time complexity, if you use an adjacency matrix, is O of B squared. And if you use an adjacency list plus a heap, it's E log V. Yeah, so this is an MS2. We can kind of verify that. It might take a minute to verify that this is actually right, but it is. So let's kind of move on, and maybe we'll see another way of thinking about it that Prims gives us. So what we do is we create an empty set. We put an arbitrary node, doesn't matter, any node we want in the set. And then while the set does not contain all the vertices of the graph, we add an adjacent vertex. It's an adjacent vertex that has the least edge weight that is not already in the set. So we can kind of think of our graph as two sets. This is the way I was taught, at least, is like you have two sets. You have like a red set and a blue set. And your red set consists of all vertices that you've already, the red set consists of all vertices you've already visited, and the blue set contains all vertices you haven't visited yet. And you're always going to choose the smallest edge weight that crosses the gap between a red node and a blue node. And then it's going to say that that new node that there's a connection to, you're going to call it red. That's how Prims works. And so we create a set, right? And let's just put A in our set. Like, okay, A is part of MST. And now we're going to say, okay, well, one of the edges between it and something from the other set, whatever's smallest, is best. So what we're going to do is we're basically kind of going to relax the edges again. So just like we saw with Bowman Ford and textures, we have to look at the edges. We're going to relax the edges. And here, B and C are the two. And because we have to choose a minimum of all the edges, that's where the use of heap comes in. So just like we saw with Bowman Ford. And adjacent, yeah, vertices are B and C. B's edge is the least weighted. So that's what's added to our set. Because B was not in our set before, so it's the least weight from something that's connected to our set by an edge, but not in our set. So we choose B. We say, okay, the edge from A to B is now part of our MST and our set of vertices is A and B. So really, like we can think of like I mentioned earlier, we can think of like A is red and B is red and C is blue. And nothing else is really colored yet because we don't have an edge to anything else yet. Like on this iteration is where we're coloring B red. But here we use green and orange, and that's also fine. I guess, yeah, let's stick with green and orange. So A is colored green, and these are colored orange. They're from the other set. So we're going to choose B. We're going to say, okay, we're going to color it green because it has the least edge weight cost of anything connected to anything from the green set. So now B becomes green, and we color everything adjacent to it orange. And now, I guess it skipped ahead of itself. It's fine. We color B green, and we relax the edges. Although when we relax edges here, we're not worried about distance from A to D. We're only worried about distance from like B to D or B.
When the class finishes. It's messy.
So then we're going to add C because C is the smallest of any of these. We don't even have to worry about sum here. It's just like 4 versus 6 versus 7. So we choose the one that's 4, and it's included. And now it's green. And now D here is orange and E is orange. So we choose the one that's smallest, 6 or 7 or 9. Well, 6 is going to be smallest. So we choose that. We choose to include D. This should be colored green. I don't know why it wasn't. And the last step, we're going to choose 4 because this 4 is the smallest edge that connects something that's green to something that's orange. And that's just how Prims works. It's greedy. At every step, it chooses the smallest edge weight. And yeah, at the end, our set will include all vertices. So we exit and it's complete. And it's going to choose all edges. It chooses all vertices, right? And each step it's going to choose the smallest edge weight. If we chose it in some other way that didn't include the smallest edge weight at each point in time, then it wouldn't give an optimal solution, because there would be, if at any point there was a better solution, like the way we can kind of prove that it's correct is we can take any other solution, and for any edge that's included that wasn't one of the ones we included, we're like, why don't we just replace with ours, which we know is less cost. So that's why it kind of a way of thinking, oh, this is why. But that's also not something that's really all that important. And yeah, so you can use prims to find the MST of a graph with which properties.
Connected, weighted, and undirected. So 2, 4, and 5.
Yep. And yeah, so those are all right. And in fact, you can also have cyclic, because cycle doesn't really matter. It's going to just remove the cycle. At the end, you'll end up with an acyclic graph. But the input can still be cyclic. But yeah, you're right. It's not direct. It will not work with direct. So, okay. So now Kruskal's. Oh yeah, and it won't work with directed because with directed, it won't, like when you use prims, the part of the reason why prims works is it kind of assumes that if something is connected to something, like if B connects to C, then it also assumes that C is connected to B. So if it's directed, it doesn't really work. Kruskal's, same requirements for a slightly different reason. Kind of assume it assumes that if they're like, if it has to be directed, because it assumes that for any 3 vertices that are all connected, there has to be a cycle. But that's only true if it's undirected. So also only works if it's undirected. And Kruskal's forms an MST by finding the least weight that don't form cycles, as opposed to prims. It's sometimes is E log E. And it creates an empty set of edges, and then it creates a list of edges sorted by least weight. And while the vertices are not connected by edges on a set, you just add the least weight edge with the other edges in the set. So the way we do this with union find, let's go back really quickly and talk about union find. So the way union find works is you have make set, which just creates a new set with some vertex in it. Union just finds the set that, if you want to union 2 sets, you find the set that X is in, you find the set that Y is in, and then you just combine them into one set. And link. So union find works really well because of like this link here. The way it actually combines them isn't just like combining them all kind of arbitrarily. It like basically builds a tree structure. So if you want to find if 2 things are connected, like find set tells you the set that X is in. So that's kind of the reason, or part of why union find is so good, is it kind of builds a tree structure in every set, so it can quickly find it. That's kind of what link does. But really, what you need to worry about with union find is it just can union sets together and quickly find which set of vertexes in. That's really it. And the way it works with Kruskal's is all Kruskal's does is at every iteration, it's just going to choose a new vertex, or it's going to choose a new edge to include. It doesn't have to connect, like you don't have to have red and blue. It's just going to create an edge between any 2 vertices which haven't already been connected. So you create an empty set of edges. And so you create an empty set of edges, and here are all the edges in the graph. And they're sorted by least weight. So A to B is C to B. They're just sorted lowest weight. This is why it takes E log E time, because actually the most expensive part of this is sorting edges. Yeah, really. And the first thing we're going to do is we're just going to take the first thing in the set, which connects 2 things which aren't already in the same set. So we say, okay, are A and B in the same set? If they aren't, then we choose that as part of our solution. And next, we're going to look at C and B. And C and B, right, are also not in the same set already. So we create a set for C and put C in B's set. And then we're going to look at D and E. They're also not in the same set. So we create a set for D, create a set for E, put them in the same set. Then the next one is B to D. B to D is the next smallest one, and they're not in the same set, so you combine them in the same set. And then for A and C, notice A and C are actually already in the same set. So we don't combine them. We don't use this edge. But then we do choose D and D. And we're done. We don't have to keep going because the entire thing is connected. So you don't have to go through the rest of the edges. So here's bullism. What is the MST of the following graph? Well, I think one easy-ish, or easy, probably the easiest way, I think maybe to do this is just go through it like Kruskal goes through it. So just pick the lowest edge or lowest cost edge, which connects to vertices which are not already in the same component. So here, now since we haven't chosen anything yet, we just choose the lowest edge weight altogether, A and B. The next thing we're going to do is we're going to look in the whole graph. What's the next smallest edge weight? Oh, it's between C and B. Are C and B already in the same component? They're not. So I choose that. Then I look for the next smallest. Well, the next smallest is a tie. It's A and C. So I could do A and C, but I really can't because they're already in the same component, right? There's already some path. Like of the edges I've chosen, there's already some path between C and A. That's how you determine if something's in the same component. And if they are, then you don't choose it. So we're not going to choose this. B and D, that's also 6. Yeah, we choose that because D is not in the same component as B. And A and E, also 6, not in the same component. We don't choose this 9 here, even though it's the next smallest, because D and C are already in the same component. We do choose E and F because they are not in the same component. And notice every vertex is connected. We have a connected graph, so we're done. So we would basically be given back, or it would return to us the initial graph minus these 2 edges. I think that's the first one. And yeah, I think that's about it. There's some code here, but yeah, this is about it for discussion today. Any questions, you're more than welcome to ask. Otherwise, that's it.
Okay, have a great night.
Thanks. You too.